Hello everyone, this is Matthew Doyle coming at you from January 22nd, 2014 on this beautiful Wednesday afternoon. It's a really nice day outside. I hope you're all having a great day. Unfortunately, I'm stuck inside working. That's a bummer. But it's good news for you because a lot of you have been asking me to make a tutorial video on ShaderFX, another one, to kind of go into more detail on how to use this great tool. So that's exactly what I'm going to do for you guys today. And what we're going to actually look at is how to create a very basic shader that includes a vertex and pixel shader and some diffuse lighting. So we're not going to go into a lot of detail. We're not going to add a texture. We're not going to add normal mapping or specularity, just purely a diffuse lit shader. And that's what you're looking at on the screen right now inside of my ShaderFX window is the final output. We're not going to be using the game surface shader. So normally that would be under hardware shader nodes, core, and then, or I'm sorry, surface shaders, traditional game surface shader. We're not going to be using that. That's got all kinds of great stuff built into it, and that's normally when you create a new ShaderFX shader, that's what's going to pop up for you, but we're not going to use that. We're actually going to create our own basic shader, and this is really exciting. So, before we actually create the shader, let's take some time to look at the final output, what the actual shader code using HLSL would actually look like. Okay, so here we have our shader code. It's a diffuseshader.fx file. That's a HLSL file, and it's not really that extensive. It's only about 50 lines of code, so if you really wanted to do this by hand, not that big of a deal. But again, remember, this is really simple shader, very simple lighting, no texturing, no normal mapping, no specular, none of the cool stuff that most next-gen shaders are going to have. Really simple stuff. But it's a good starting point if you're just now learning about shaders. All right, so before we go line by line and look at some of this code and talk about what it does, let's briefly talk about how you take a 3D object that you've built in MyLT and represent it in the game world. Okay, so in order for a 3D object to be represented in 3D space, such as an object you model in MyLT, so let's just draw a cube here. This could be our 3D object that we just built in MyLT. It's really impressive, I know. All right, so here's our 3D object. Right now, it's in what we would call object space or model space. All right. Now, in order to get that to display on the screen, we need to do some math that well, we call it matrix multiplication, and we had to go through several stages to get it to the final output, which let's just draw over here. This is our screen. All right. Now we'll call that screen space. Now before we can get it to screen space, what we're going to need to do is we're going to need to go to world space. All right, so world space, we'll draw, I don't know, a planet here. Here's some land. This is our world space. Now world space is basically where the 3D object lives. And once we've got it into world space, we can then use another matrix multiplication to translate it from world space into view space. All right, and view space is basically where our camera is. All right, so the camera is our view space. You could also call it camera or eye space. It could be your eyes instead of a camera. All right, now once we've used the matrix multiplication to get it to view space, finally we can go into screen space with another matrix multiplication. You can also call this projection. All right, so we'll just write that down here, projection. All right, so that's how we get our 3D object that we build in MyLT to be represented on the screen as a 2D object with perspective distortion, right? So we go from object space to world space to view space and finally to screen space. Now, the way we do that, again, as I said, is with matrix multiplication. Let's look at the code now. First of all, inside of our code, we have our variables. At the top here, we're going to see four very strange looking variables. But these are the actual matrices that we use to move that object from object space, model space, to world space, to view space, to projection or screen space. And you'll notice they're float 4 by 4. That means they're floating point numbers, but they are a two-dimensional array or a matrix of 4 rows by 4 columns. All right. So if I were to represent that in a mathematical notation, my matrix would look something like this. All right, so you draw brackets, then you have your values. All right, and you get the idea. All right, so that's basically a matrix. It's basically a row, column ordered uh, grouping of numbers. All right, and you really don't need to know that much about it if you're not going to be doing this stuff by hand. But I just wanted to give you some theory behind this. All right, so we also have another matrix here, world inverse transpose, and this one's going to be used for our lighting calculations when we actually add diffuse lighting. Next, we have variables for our ambient light. So we've got ambient color and ambient intensity, so that's the brightness of our ambient light. And then we have three variables for our diffuse lighting. We have a float 3, a float 4, and a regular float. And now bear in mind that these things, float 3 and float 4, they just represent the number of floating point values for that particular. It's basically a vector, right? So it's a this is a vec 3, this is a vec 4. That means it has three inputs or three properties. So a vector could be an XYZ value. That would be something good for representing a space in 3D. So that would be a float 3. And then a float 4 would be a XYZ and W value. So that would be a four-dimensional vector, or a vector in four-dimensional space, right? So we have our diffuse light direction, diffuse color, and our diffuse intensity. Now, ultimately, what you'd want to do in a next-gen shader is have your lighting brought in by the actual application, the game, rather than hard coding your light's values inside of the shader. But this is a very simple shader we're putting together, and in order to do something like that, it requires a little more finagling and understanding. So we're not going to be doing that. We're going to be hard coding where our diffuse light is coming from. Next, we have a couple of structures. We have our Vertex Shader input. This is basically what's going to come from the game, from the application. It's automatically going to fill this data for each vertex in the 3D model. Likewise, these matrices up here, they are automatically populated by the application. You don't have to figure out all the matrix math yourself. You don't have to put all that in. The application or your game should do that for you. All right, so back down here we have the Vertex Shader output. This is another object that will be spit out by our Vertex Shader. So above the input we're going to get from our game map, we're going to get the position of the vertex, we're going to get the normal of the vertex, and then it's going to do a bunch of cool stuff on that, and when it's done, the Vertex Shader will spit this out. And when it spits it out, it's going to spit out the position again, because we may transform the position. But instead of the normal, we're going to spit out the color of the vertex. All right? So moving down to the actual Vertex Shader, here's our Vertex Shader. So you can see what we're going to do. We've got our Vertex Shader output, right? That's going to be our final result. We've got our Vertex Shader input coming in as an argument to our function. And then all we do is we calculate the position of the vertex and the color of the vertex. So here, line 1 is our first transform, our first matrix multiplication. So we get our world position of the object, our 3D object that we modeled in MyLT or whatever, and we multiply that object's position or its vertices position, because remember this Vertex Shader is being run for every vertex in the object. So we get the position of that vertex and we multiply it by the world matrix, and that gives us our world position. Next, we want to multiply that result, the world position, by our view matrix, and that gives us the view position, how it relates to the camera. And finally, we want to take the view position and multiply that, doing matrix multiplication again here, using multiply, by the projection matrix, and that will give us the final perspective matched screen space position, what you see on the screen. Now, once we do that, we store that in our output value here. Once we do that, we can do the color. So the color is going to basically take the normal direction. We're going to use some more matrix multiplication here. We're going to get the normal direction of the vertice, and we're going to multiply that by the world inverse transpose, and that's going to give us our normal for that vert. Now for the light intensity, we're going to use a dot product. Basically, we're going to do the normal and the diffuse light direction. As you recall, the diffuse light direction is hard-coded up here. So the dot product allows us to get basically the light intensity using the angle of incidence from the vertex's normal and the direction that the light is coming from. Finally, we get our output color using, we're going to do a saturate operation, and the saturate will be applied to the diffuse color, again hard-coded. We're going to multiply that by the diffuse intensity, also hard-coded, and we're going to finally multiply that by our light intensity, where the calculation is done up here. And that's it. That's our vertex shader. Then we pass that information automatically gets passed on to our pixel shader. And then our pixel shader simply does another saturate operation. And this time we take that color, our vertex color, we're going to add the ambient color, which is hard-coded, and we're going to multiply that by the ambient intensity, also hard-coded. You're not going to want to hard-code your diffuse or ambient lighting in the shader normally, but again, this is a good starting point for you to understand how this all works. Finally, we have our technique, and we're going to call this technique Diffuse Light Shader. So you can have multiple techniques in a shader. In this case, we only have one technique. And then inside of the technique, you can have multiple passes. And all the pass really tells us here in this case is that we want to compile our vertex and pixel shaders for Vertex Shader 2.0 and Pixel Shader 2.0. All right, so I know if you're not big on math or don't know anything about code, this was probably all Greek to you, but it's a good idea to at least get some of the theory behind how this all works, so that when you're actually doing this in ShaderFX, you'll have kind of a better understanding of what it is you're doing. Alright, so now we've got all that boring theory and yucky math out of the way. We can actually get into the fun stuff using the ShaderFX tool. So we're going to go ahead and just apply our shader to this entire collection of meshes here. Our character, I'm just going to assign him a new material, ShaderFX, and we'll just open the ShaderFX window. I'm going to maximize my viewport here. As I said before, when you create a new ShaderFX shader, it's going to automatically be populated by this traditional game surface shader and this output material here, which is great. It's got all the things you're going to want to use in a next-gen shader, reflection, IBL, normal mapping, emissive, all that cool stuff. But for the purposes of our tutorial, we don't need that, so we're going to delete it. You're going to notice that when I try to delete it, nothing happens. I'm hitting delete on my keyboard, mad as a crazy, I don't know, a crazy something, but I'm hitting it a lot, nothing's happening. The reason is that's because I'm not in advanced mode. So toggle advanced mode. Once you do that, you're going to see these little rectangles at the top of each node. That allows you to go into the node to see what it's composed of. Scary, don't get scared though. Alright, now once I'm in advanced mode, I can actually delete that. And now we have a nice clean blank slate. Now, I don't have my attribute editor open in my LT, which means that I can't necessarily edit the node's properties when I add them. However, I can go into settings and show the property panel, and now I'll be able to do so from the ShaderFX window without having my attribute editor open. So I'm going to start from the end of my shader and work my way towards the beginning. You could also work from the beginning to the end, but you'll see what I mean here in a second. What I'm going to do is I'm going to create my first node, or I should say my last node in the shader, by going to Hardware Shader Nodes, Core, Hardware Shader. Now this is my final node. This is my output node. This is what's going to spit out all the code, and everything will funnel into it. That's what I mean by starting from the end. So we're just going to change the shader config to HLSL5. So we'll call this my diffuse shader.fx. Okay, that's all we really need to do with that node. So let's go ahead and move on to the next one. We're going to we need to add our technique. As you recall, there was one technique. That's going to be found once again under Core, Technique. And I'm not going to wire them up yet, but I'm going to give my technique a name. We're going to call it Diffuse Lighting. Next up, we're going to need our pass. As you recall from the shader, we had one pass, also under Core. And once again, I'm not going to wire this up yet, but we're going to name it Pass 1. Next up, we need our Vertex Shader, also under Core. All right, and this represents the actual Vertex Shader function. And then we need our Pixel Shader, also under, you guessed it, Core. And this represents the Pixel Shader function. Okay, so we've got our core nodes here. This basically represents the primary structure of our Pixel Shader. We've got our Vert and Pixel Shader functions. We've got our pass, our technique, and the output, which really doesn't represent necessarily anything inside of the shader itself, but this is how we'll save the shader to disk and choose the shader language to compile for. All right, we're moving right along. Let's go ahead and begin building our vertex shader. We're going to start with the vertex position. As you recall, we need to take the vertice positions from local space or model space, also object space, and translate those positions all the way into screen space or projection. And of course, we have the intermediary stages that we have to go through to get it there. So let's go ahead and get started with that. We're just going to move over here to the left of the ShaderFX window. And we need to start out with the actual vertex position input from the model itself. So we're going to go to Hardware Shader Nodes and then Input Application. That is, anything from this area is going to be given to us from the app or your game. And we want vertex position. And this will give us the actual coordinates in 3D space, in object space of our mesh. And then we're going to output that into a texture coordinate. That's going to be found under core, to a texture coordinate output. And this is going to allow us to create a variable that we can then use as part of our vertex shader function. So we're going to wire the vertex position object space into the x, y, z, w coordinates of our texture coordinate output. You'll notice the color there is pink, and basically that's a float 4. So these two match up, so that's what we want. Now I'm going to, in the properties panel, I'm going to name this texture coordinate output. I'm going to call it vertex shader input. We'll just call it that. Right? Now for the texture coordinate name, we're going to call this position. And we need to change the texture, the semantic type where it says texture coordinate. Let's scroll that out a little bit. We're going to change that to SV position, SV underscore position. Now if we jump back over to the code, well, let's go ahead and give the name for our semantic first, and let's name it position. So if we jump over to the code again and we look at the vertex shader input structure, we can see our two variables. We're working with the first one here, position. All right, and then after the word position, that's the variable name, you'll see a colon, and in this position 0, that's a semantic. That's something that you don't really necessarily need to know a lot about right now, but if you want to look it up, look up semantics. All right, so that's going to represent our vertex shader input, that is getting the data from model space, from the object, into our vertex shader. And all we need to do is wire that directly into our vertex position input on the vertex shader node. So let's just drag these guys down here. Next we need our vertex position output. So to do that, it's going to be a very similar process, but in this case, this is the part when we output, we want to output the vertex position that we've received from the model. We want to output that after it's had all that wonderful matrix multiplication done to it to get it into screen or projection space. So once again, we're going to need a vertex position, and we can just Control D to duplicate that. And that gives us our original vertex position. And now we're going to need to go, as you recall, what was the first transform we needed to do? We needed to do some matrix multiplication to get it into world position or world space. So we're going to do exactly that. We're going to add a multiplication node. So we'll go to Hardware Shader Nodes, Math, Multiply. And then we'll wire in our object space into that multiply operation. And now we need the world matrix. So that's going to be found under matrices. And then there it is, world. So we see here we've got our 4x4 matrix. That's the one we want. And we'll just wire that into the second parameter of our multiply operation. So now we're multiplying the object space coordinates of the verts by the world space matrix. After world space, what was next? That was view space, our camera space. So once again, we're going to do a multiplication. Now we could go in here and find multiply, or we could just select it, hit Control D, and we'll wire that into the first parameter. And then we need our view matrix. So that's under matrices and then view. Once again, a 4x4 matrix. You can see the little camera there. Lets you know that we're talking about the camera's view or the eye view. And we'll just wire that into our second parameter there. And finally, we need to go to screen space or projection. So we'll go to matrices again, and we'll look for projection. And there it is. Also a 4x4 matrix, and we'll need our multiply. Just the same, repeating here. Very simple actually to do. All right, and that is going to do it. So we'll go ahead and just grab all of that. And we need to now connect, just like we connected the vertex position to a texture coordinate output, we're going to do the same thing here. So we'll just go to hardware shader nodes, core, texture coordinate output, and we'll wire that into the X, Y, Z, and W. Now in this case, it's going to be identical. We're going to name it Vertex Shader Output, and the texture coordinate name will once again be position. Semantic will be also position, and we'll change the type once again to SV position, and then we'll turn on tweak texture coordinate. And this can be wired into the vertex position output. Now, this is good because at least you see step by step how we do the transform from object space all the way to screen space, and then put that into our vertex shader. However, there is a shortcut inside of ShaderFX. You don't have to do this yourself. You could simply go into hardware shader nodes, matrices, and then find world view projection. This will go all the way between world view and projection. All you have to do is multiply the vertex position here by this instead, and it will do everything for you, all three of these. However, we're going to go ahead and stick with the way we did it here. One thing I want to correct though is I made a little mistake, imagine that, but on my texture coordinate outputs I put the semantic as position for both of them, and that changes semantic type to custom semantic. That's not actually what I want, so I'm going to delete semantic and change the drop down to SV position for both of these. Alright, so now when I click on them they should both say SV position as a semantic type. So now let's wire these guys back in here, vertex input and vertex position output. And now we can wire that into our vertex shader on the pass. Now before we actually add the diffuse lighting for our vertex lighting, let's go ahead and add our pixel shader, or at least part of it. Now what we're going to do for our pixel shader for now is we're just going to give it some ambient color. So to do that we'll go to hardware shader nodes, value color, and we'll give this node a name of ambient color. Next we'll want to be able to control the intensity of our ambient light, and we'll do that with a floating point value. And what we're going to do is we're going to use this value, we're going to multiply it by our RGB alpha on our ambient color to give us the intensity of our ambient light. Now again, in a next-gen shader normally this stuff would be actually controlled by the application ambient lighting, but we're going to hard code it into our shader for this. So we'll do a multiplication and we'll do RGB alpha times our float, and let's give our floating point value a name, call it ambient intensity. There we go. And for our multiply operation, let's call this ambient contribution. Perfect. So we're just going to leave that as is, and we're going to wire that into the pixel color. Eventually we're going to need to get the diffuse lighting contribution as part of that, but let's just do ambient for now. Wire this into our pixel shader on the pass. Wire the pass into our diffuse lighting technique. And finally our output, and there we go. We have our shader, a very flat shaded guy, controlled only by our ambient lighting so far. So if I were to change the ambient light color here to something else, you can see there the effect it has. I can also control the intensity here. So let's go down to 0.25. We can see the effect there with the pixel shader. Okay, so let's move on and let's add our actual diffuse lighting. But before we do that, why don't we go ahead and spit this out as an actual shader file and see what it looks like so far. So we'll select the hardware shader node and we'll choose save to disk. Here we are inside of the actual output shader file that ShaderFX spit out for us, and you're going to notice that it's not exactly the same as the original shader file, the HLSL file that we looked at, but it is close enough. It does basically have the exact same code. In fact, we look here, we see our projection and view matrices, our world matrix, and then we have our vertex shader input structure, our vertex shader output structure, then our actual vertex shader, and our pixel shader, and finally our technique and our pass. Now, one thing you may notice is that inside of our vertex shader, our matrix multiplication to go from model space to world space to view space, and view space to screen or projection, the names of the variables are not very descriptive. Multiply op 53, 54, and so forth. Now, that's because we didn't name those multiply operations inside of ShaderFX. So let's go ahead and do that. Let's name them to something more meaningful. Okay, so here are 3 multiply operations, and in the properties panel we've changed the names. Instead of them all saying multiply op, mult op, they now say world position, view position, and projection position. So now if we output our file again, we can see that those variable names have been changed to match the name of our node. Alright, so let's go ahead and do the last step here. Let's add our diffuse lighting. So we'll find a nice clear area up here. Now for lighting, we need the vertex normal input from the application. So we're going to go to Hardware Shader Nodes, Inputs Application, Vertex Normal. We're also going to need that other matrix. Remember World Inverse Transpose? So we're going to go get that under Matrices, and you'll find it World IT for World Inverse Transpose. And what do? When we have a matrix in our verts, to transpose those, or I should say translate those verts into that space, we're going to use a multiply operation. Now in this case, we're just going to multiply this XYZ, and then we're going to multiply it by our matrix. Now we also want a semantic, a variable, to represent our vertex normal. So if you recall, if we jump back into our code for our diffuse shader, inside of our shader input, we have this variable here, this property, normal, with a semantic normal. So we need to go ahead and create that. So we'll create a hardware shader node, core, texture coordinate output, and we're going to bring out the vertex normal, which is a float 4, and plug it into the XYZW here. And we'll just go ahead and name it up here normal. And we'll change the semantic type to normal. There we go. So now we need to get the light's direction and do a dot operation on the direction of the light from the vertex position, and that's done very easily using the dot product node. So we go to Hardware Shader Nodes, Math, dot product. I'm not going to explain dot products in detail or anything. You might want to look that up if you don't remember that from some of your math classes. But it's not really that difficult to understand. So anyway, we're going to go ahead and continue on. We need to add our actual diffuse light direction. Now normally, as I said, in a next-gen shader, the light direction would be actually taken from the application, the lights inside of it. But we're just going to hardwire, we're going to pretend like we've got a light and hardwire it inside of our shader for this. So we'll go to Hardware Shader Nodes. We're going to use a value of a float 3 to represent the direction of our light. Now we're going to wire in the result of our multiply operation here, our world inverse transpose matrix multiplication, into the top of our dot product, and our light direction will go into the bottom. And now we'll be able to adjust this light direction. Let's go ahead and give it a name. We'll call it diffuse light direction. We'll be able to adjust this floating point value. We've got X, Y, and Z values to basically rotate the light around the object. And those values can be either negative or positive. Alright, so now that we've got our light direction, we're going to need our diffuse color and its intensity. So let's add a diffuse, let's add a float 4. And this floating point value here will represent our diffuse color. So let's name it that. Alternatively, we could use the value color. And instead, we'll delete that float 4, and we'll call this diffuse color. Just easier to change the color that way. Now we need our diffuse intensity, so that can be a float. And we're going to multiply those together. So we're multiplying the RGB alpha value of our color with the intensity. And if we want to be able to access the intensity and the light direction from the Maya LT attribute panel without coming into the window, we'll just make sure that input from Maya is turned on for both of these nodes. Okay, and now we just need to actually multiply this light intensity. We're going to name this, instead of dot op, we're going to change this to light intensity. So we get a nice variable name inside of our shader. And we're going to name this multiply operation normal. Now we're going to multiply our diffuse contribution. So let's name this up here diffuse contribution with our light intensity. And we're going to call this light contribution. All right. So one last step, we're going to use the saturate node. That's going to be found under math and saturate. And this is going to clamp the lighting contribution between a value of 0 and 1. Kind of like normalizing, I guess. So finally, we need another texture coordinate output. That's under core again. And we'll wire that into the X, Y, Z, and W. And in this case, we're going to give it a name of color. And the semantic we're going to use, the type, will be color. And there we go. Going back just briefly, once again, we first of all need to get the vertex normal position of our verts, and then do some matrix multiplication using world inverse transpose. And we'll do a dot operation with that normal and the light direction. Now, if you want to Google this, you're going to find it under L.N. That's the lighting direction, the dot product of the light direction, and the normal of the verts. So just look for L.N on Google, and if you don't remember how to do dot products, just obviously Google dot products. But the great thing is you don't need to know those things if you don't want to, because ShaderFX is doing all that math for you. Good to understand the concepts, though. All right, so all we're really doing is we're getting that dot product, and then we're going to use that dot product. We're going to multiply that with our diffuse light to give us our total lighting contribution. So this is going to allow us to have a directional light in our scene, a light that shines from one direction. And then finally, we're going to clamp that value between 0 and 1 and create a semantic for it that we can work with inside of our shader. Now you may be wondering how we get this lighting contribution, our vertex lighting, into this, our vertex shader, because the only two inputs here are the position input and the position output, and we can't really wire the lighting contribution into our vertex positions. That's where the process box comes in. So we'll go ahead and connect the texture coordinate output into the process input here. And what that's going to do is that's going to actually add that code that represents these nodes, the actual shader code, into the vertex shader function. Now, last of all, we need to take that same data and plug it into our pixel shader so that we can add our diffuse lighting to our ambient. And we're going to do that using an add operation. So once again, under math, very simple to find, add. All right, and then we're going to wire in the output from our texture coordinate output up here into our add operation at the top. And then we're going to wire in our ambient contribution to the bottom of that. We can get rid of this one. We'll just drag this result into our pixel color to do that. And right away you can see our shader in its completed form. So we can see we're getting some directional light. And I'll go ahead and close this down. Let's bring up the attribute panel. And as I set those to input from Maya, we can see our diffuse intensity and diffuse light direction are available here. So now if I change the intensity, you can see the change there. Likewise for the light direction, I can make some adjustments here, and you can see that the light changed direction. Set it to -1, and now it's on the back side of him. Alright, so like I said, you're not going to want to normally do this, hard code the light direction and whatnot into your shader, but for the purposes of our demonstration and tutorial tonight, I think this is going to work for us. All right, so we're done today. I think we've got a lot of progress here, and I think you guys probably have learned a lot about building your own basic shaders using ShaderFX, as well as some of the theory behind shaders and the math, the yucky math. You know what? If you don't like math, just pretend like you didn't hear that part, and just move along. Just move along. Nothing to see there. But anyway, you've got the point here of creating a nice diffuse lit shader, and I think the next step would just be to maybe add some specular or even a texture and normal map, and that's not much harder than what we've already done here today. So maybe that's what I'll do for the next blog post if you guys ask really nicely. But if you have any comments or questions, just post them in there and I will get back to you with those answers as soon as possible. So this is Matthew Doyle signing off. We'll see you next time.